Hello students. Today we are going to cover some of the most important and expected questions from Unit 1, Elementary Concept and DC Circuits. These questions often come in your exams, so let's keep our focus sharp and understand them in a simple way. First, let's talk about the resistance of a material. Resistance is the property of a material that opposes the flow of electric current. It depends mainly on four factors: the length of the conductor, the cross-sectional area, the type of material, and the temperature. A longer conductor has more resistance, a thicker conductor has less resistance, and different materials resist current differently. Also, temperature plays a key role as it can increase or decrease the resistance. Alright, let's move on to our next important topic: temperature coefficient of resistance. From this topic, we can expect questions such as define temperature coefficient of resistance and write its unit. Temperature coefficient of resistance, often called TCR, tells us how much the resistance of a material changes when its temperature changes by 1 degree Celsius. Its unit is per degree Celsius. For most metals, resistance increases as temperature increases, so they have a positive TCR. Alright, let's move on to our next important topic: factors affecting resistance. From this topic, we can expect questions such as state the factors affecting resistance and explain the temperature dependence of resistance. Resistance mainly depends on length, area, material, and temperature. As the temperature increases, most metals show higher resistance because atoms vibrate more, making it harder for electrons to flow. However, some materials like semiconductors behave differently, and their resistance decreases with increasing temperature. Alright, let's move on to our next important topic: Ohm's law. From this topic, we can expect questions such as state and explain Ohm's law. Ohm's law states that the current through a conductor is directly proportional to the voltage across it and inversely proportional to its resistance, provided temperature remains constant. Mathematically, it is written as V equals I multiplied by R. This law is the foundation of almost all circuit analysis and helps us understand how voltage, current, and resistance are related. Alright, let's move on to our next important topic: lithium-ion battery. From this topic, we can expect questions such as explain the construction and working principle of a lithium-ion battery. A lithium-ion battery has two electrodes: a positive electrode made of lithium compound and a negative electrode usually made of carbon. An electrolyte allows lithium ions to move between the two electrodes during charging and discharging. When the battery charges, lithium ions move from the positive to the negative electrode and store energy. During discharge, they flow back to provide power to devices. Alright, let's move on to our next important topic: energy consumption. From this topic, we can expect questions such as the electrical load of a bungalow is given. Calculate daily energy consumption and the monthly electricity bill. Energy consumption is calculated by multiplying the power of each appliance by the hours it is used each day. The total daily energy use in kilowatt-hours is then multiplied by the number of days in a month to find the monthly energy used. Finally, multiplying this value by the electricity rate per unit gives the monthly electricity bill. Alright, let's move on to our next important topic: active and passive networks. From this topic, we can expect questions such as define active and passive network and lumped and distributed network. An active network contains at least one source of energy like a battery or generator, while a passive network has only passive elements like resistors or capacitors. Lumped networks have elements like resistors and capacitors that are clearly separated and concentrated at specific points in a circuit, whereas in distributed networks, these elements are spread out along the length of the component, like in transmission lines. Alright, let's move on to our next important topic: linear and nonlinear networks. From this topic, we can expect questions such as define linear and nonlinear network and unilateral and bilateral network. A linear network follows Ohm's law, meaning its current changes proportionally with voltage. A nonlinear network does not follow this proportionality. A unilateral network allows current to flow only in one direction like a diode, while a bilateral network allows current to flow equally in both directions, such as a resistor. Alright, let's move on to our next important topic, delta to star conversion. From this topic, we can expect questions such as, obtain the formulae for converting a set of given delta-connected resistances into an equivalent star connection. To convert a delta network to a star network, each star resistance is calculated by multiplying the two adjacent delta resistances and dividing by the sum of all three delta resistances. This makes analysis simpler in many circuits. Alright, let's move on to our next important topic, star to delta conversion. From this topic, we can expect questions such as, derive the equations to convert a delta-connected resistive circuit into an equivalent star circuit. In a star-to-delta conversion, each delta resistance is found by adding the product of two star resistances and dividing by the third star resistance. These conversions are essential for simplifying complex resistor networks. Alright, let's move on to our next important topic, Kirchhoff's laws. From this topic, we can expect questions such as, state and explain Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law states that the total current entering a junction is equal to the total current leaving that junction. Kirchhoff's voltage law states that the sum of all voltages around a closed loop in a circuit is zero. These laws help us analyze complex electrical circuits systematically. Alright, let's move on to our next important topic, loop analysis. From this topic, we can expect questions such as, find the current flowing through using Kirchhoff's loop analysis for the given circuit. In loop analysis, we apply Kirchhoff's voltage law to each loop of the circuit and set up simultaneous equations to find the unknown currents. It is a powerful method for solving circuits with multiple loops. Alright, let's move on to our next important topic, superposition theorem. From this topic, we can expect questions such as, find the current flowing through a 3 ohm resistor using superposition theorem. The superposition theorem says that in a linear circuit with more than one source, the current through any element is equal to the sum of the currents produced by each source acting alone, while all other sources are replaced by their internal resistances. Alright, let's move on to our next important topic, insulation resistance. From this topic, we can expect questions such as, define insulation resistance and derive an expression for insulation resistance of a single-core cable. Insulation resistance is the resistance offered by the insulating material of a cable to prevent current leakage. For a single-core cable, it depends on the length of the cable, the resistivity of the insulating material, and the ratio of outer to inner diameters. This ensures safety and minimizes energy loss in cables. That's all for today's session. These are the most important and expected questions from this unit that you should focus on for your exams. If you revise these topics carefully and understand the concepts, you'll be ready to answer confidently in your upcoming semester exams. Students, now we are going to learn the most important questions from Unit 2, Electromagnetism. These topics are very important for your semester exams, so let's go step by step in a simple and exciting way to make sure you understand everything clearly. Let's begin with reluctance. Reluctance is the opposition offered by a magnetic material to the flow of magnetic flux. It is similar to resistance in an electric circuit, but for magnetic circuits. Its unit is ampere-turn per Weber. It depends on 3 factors: the length of the magnetic path, the cross-sectional area of the material, and the type of material used. Alright, let's move on to our next important topic, magnetic field strength. From this topic, we can expect questions such as, define magnetic field strength and write its unit and the expression for magnetic field strength at any point in the field produced in a solenoid. Magnetic field strength shows how strong the magnetic field is at a particular point. It is defined as the magnetomotive force per unit length of the magnetic path. Its unit is ampere-turn per meter. In a solenoid, which is a coil wound in the form of a cylinder, The magnetic field strength is given by H equals N times I divided by L, where N is the number of turns, I is the current, and L is the length of the solenoid. Alright, let's move on to our next important topic, relative permeability. From this topic, we can expect questions such as, an iron ring of mean circumference of 150 centimeters and cross-sectional area of 12 square centimeters is wound with 600 turns of coil carrying a current of 2 amperes and producing a flux of 1.25 milliweber. Find the relative permeability of iron. Relative permeability is a measure of how easily a material allows magnetic flux to pass through it compared to air. In such problems, we use the formula R equals B divided by shunya times H, where B is flux density, shunya is permeability of free space, and H is field strength. Alright, let's move on to our next important topic, relative permeability, in a second coil problem. From this topic, we can expect questions such as, a coil of 500 turns is wound on an iron ring of circular cross-sectional area of 3 square centimeters and mean diameter 20 centimeters. The magnetic flux is 0.5 milliweber when the coil carries 2 amperes current. Determine the relative permeability of the material. This problem also follows the same steps of finding flux density and field strength, and then using the formula for relative permeability. Alright, let's move on to our next important topic, electric versus magnetic circuit. From this topic, we can expect questions such as, distinguish between an electric circuit and a magnetic circuit, stating similarities and dissimilarities. An electric circuit carries electric current, while a magnetic circuit carries magnetic flux. Both have similar quantities like electromotive force compared with magnetomotive force and resistance compared with reluctance. However, in an electric circuit current actually flows, whereas in a magnetic circuit no charges move, only magnetic flux exists. Alright, let's move on to our next important topic, electromagnetic induction. From this topic, we can expect questions such as, what is electromagnetic induction, and state Faraday's laws of electromagnetic induction. Electromagnetic induction is the process of generating an electromotive force in a conductor when it is placed in a changing magnetic field. Faraday's first law states that an EMF is induced whenever there is a change in magnetic flux linked with a conductor. The second law states that the induced EMF is directly proportional to the rate of change of magnetic flux. Alright, let's move on to our next important topic, magnetic effect of electric current. From this topic, we can expect questions such as, what is the magnetic effect of an electric current in case of a long straight conductor, and state the right-hand thumb rule. When a current flows through a straight conductor, it produces a circular magnetic field around it. The direction of the field is given by the right-hand thumb rule, which says that if you hold the conductor in your right hand with the thumb pointing in the direction of current, then the fingers curl in the direction of magnetic field lines. Alright, let's move on to our next important topic, self-inductance and EMF. From this topic, we can expect questions such as, two perfectly coupled coils have 800 and 600 turns respectively. A current of 2 amperes flowing through the first coil produces a flux of 5 milliweber in it. Calculate self-inductance of the first coil and EMF induced in both coils if the current is turned off into milliseconds. Self-inductance measures how much EMF is induced in a coil due to the change of current in the same coil. We use L equals N times divided by I for self-inductance and E equals minus L times change in I over change in time for induced EMF. Alright, let's move on to our next important topic, force on a conductor. From this topic, we can expect questions such as, a conductor of length 10 centimeters carrying 5 amperes is placed in a uniform magnetic field of flux density 1.25 Tesla. Find the force acting on the conductor if it is placed along, perpendicular, and at an angle of 30 degrees to the magnetic flux. The force on a current-carrying conductor in a magnetic field is given by F equals B times I times L times sin theta. If the conductor is along the magnetic field lines, sin theta is 0 and force is 0. If perpendicular, sin theta is 1 and force is maximum. At 30 degrees, the force is reduced because sin 30 degrees is 1/2. Alright, let's move on to our next important topic, mutual inductance. From this topic, we can expect questions such as, two coils having turns 1000 and 1500 are placed on a common magnetic circuit. A current of 5 amperes in coil 1 produces a flux of 0.2 milliweber and 80% of this flux links coil 2. Find self-inductance of coil 1, mutual inductance between them, and the EMF induced when the current in the first coil is interrupted in 0.01 seconds. Mutual inductance shows how much EMF is induced in one coil when the current in a nearby coil changes. We calculate it using M equals N2 times 2 divided by I1. Alright, let's move on to our next important topic, steel ring problem. From this topic, we can expect questions such as, a steel ring has a mean diameter of 40 centimeters, a flux density of 0.9 Weber per square meter, a magnetic field intensity of 3500 ampere per meter, cross-sectional area of 15 square centimeters, and a coil of 440 turns. Calculate the exciting current and the self-inductance. Here, we use the relationships between B, H, and the number of turns to find the current and self-inductance. Alright, let's move on to our next important topic, induced EMF in a coil. From this topic, we can expect questions such as, a coil of 150 turns is linked with a flux of 0.01 Weber when carrying a current of 10 amperes. Calculate the induced EMF if the current is uniformly reversed in 0.1 seconds and then interrupted in 0.05 seconds. The EMF induced in such cases is found using the formula E equals L times change in current over change in time. Alright, let's move on to our next important topic, mutually induced EMF expression. From this topic, we can expect questions such as, obtain the expression for the mutually induced EMF in a coil when the neighboring coil is excited by a current, and describe the circuit diagram with notations. We explain that mutually induced EMF is produced when the magnetic field created by one coil links with another coil. Alright, let's move on to our next important topic, coefficient of coupling. From this topic, we can expect questions such as, obtain the expression for the coefficient of coupling of two magnetically coupled coils. The coefficient of coupling tells how much of the magnetic flux from one coil actually links with the other coil. It is the ratio of the actual linked flux to the maximum possible flux. Alright, let's move on to our next important topic, coils with given inductance. From this topic, we can expect questions such as, two coils A and B have self-inductance of 10 microhenry and 40 microhenry respectively. A current of 2 amperes in coil A produces a flux linkage of 5 microweber turns in coil B. Calculate mutual inductance, coefficient of coupling, and the average EMF induced in coil B if the current of 1 ampere in coil A is reversed at a uniform rate in 0.1 second. This problem applies all the formulas for mutual inductance and induced EMF with the given values. Alright, let's move on to our next important topic, energy stored in an inductor. From this topic, we can expect questions such as, derive an expression for energy stored in an induct and hence obtain energy stored per unit volume of it. The energy stored in an inductor is given by half Li squared. This energy is stored in the magnetic field around the inductor. Energy per unit volume is this energy divided by the volume of the magnetic field region. Alright, let's move on to our next important topic, toroid problem. From this topic, we can expect questions such as, an air-core toroid has a mean diameter of 25 centimeters, a circular cross-sectional area of 6.26 square centimeters, and is wound uniformly with 1000 turns of wire. Find the inductance of the toroid, the induced EMF when current increases at 200 ampere per second, and the energy stored in its magnetic field when the coil carries a current of 10 amperes. A toroid is a coil shaped like a ring, and we apply formulas for inductance, induced EMF using rate of change of current, and energy stored in its magnetic field to solve such problems. That's all for today's session. These are the most important and expected questions from this unit. If you focus on understanding these key concepts and practice the numerical problems, you will be confident and well prepared for your semester exams. Hello students. Today we will explore the most important questions from Unit 3, AC Fundamentals. These topics are crucial for your semester exams, and I will explain them in a simple and clear way so that you can understand them easily. Let's begin with the first question. Define instantaneous value, maximum value, and average value in case of a sinusoidal alternating quantity. Instantaneous value is the value of the alternating current or voltage at a particular instant of time. Maximum value is the highest positive or negative value the waveform reaches in one cycle, also called peak value. Average value is the average of all instantaneous values of the waveform over a half cycle, because the average over a full cycle is 0 for a pure sine wave. Alright, let's move on to our next important topic, mathematical and graphical representation. From this topic, we can expect questions such as, explain the mathematical and graphical representation of an AC waveform. A sinusoidal AC waveform can be represented mathematically by the equation I equals I max sine omega t, where I max is the maximum value, omega is angular frequency, and t is time. Graphically, if we plot current or voltage on the vertical axis and time on the horizontal axis, we get a smooth wave rising to a positive peak, returning to 0, dipping to a negative peak, and again returning to 0 to complete one cycle. Alright, let's move on to our next important topic, cycle, period, and frequency. From this topic, we can expect questions such as, define cycle, period, and frequency in AC waveforms with suitable examples. A cycle is one complete set of changes of the waveform from 0 to positive maximum to 0 to negative maximum and back to 0. The period is the time taken to complete one cycle, measured in seconds. Frequency is the number of cycles completed in 1 second, measured in hertz. For example, in India the power supply frequency is 50 Hz, which means the wave completes 50 cycles in 1 second. Alright, let's move on to our next important topic, RMS value. From this topic, we can expect questions such as, explain the significance of RMS value in AC circuits and derive its formula for a sinusoidal waveform. The RMS value or root mean square value of an alternating quantity is the value of direct current that would produce the SAM heating effect as the alternating current in the SAM resistor. For a pure sine wave, RMS value is maximum value divided by root 2. It is significant because it helps in measuring the effective value of AC for power calculations. Alright, let's move on to our next important topic, peak factor and form factor. From this topic, we can expect questions such as, define peak factor and form factor and derive their mathematical expressions. Peak factor is the ratio of the maximum value to the RMS value. Form factor is the ratio of the RMS value to the average value of the waveform. These two factors help in analyzing the shape and behavior of the waveform. Alright, let's move on to our next important topic, instantaneous current problem. From this topic, we can expect questions such as, an alternating current has a frequency of 50 Hz and an RMS value of 10 amperes. At time 0, its instantaneous value is plus 5 amperes and increases in magnitude. Derive the expression for its instantaneous value and calculate the current at 0.01 second and 0.015 second and sketch the waveform. In such problems, we use the formula I equals I max sine omega t plus or minus phi, where phi is the phase angle. The current at given times can be calculated by substituting these values into the equation. The waveform is sketched as a sine curve showing the calculated points. Alright, let's move on to our next important topic, waveform equation problem. From this topic, we can expect questions such as, the equation of an alternating current is given by I equals 42.42 sin 628 t. Calculate the maximum value of the current, the frequency, RMS value, average value, and form factor. Here, we know the equation is in the form I equals I max sin omega t. From the given constant, we find I max directly. Frequency can be found using omega equals 2 pi f. RMS value is I max divided by √2 and average value is 0.637 times I max for a sine wave. Alright, let's move on to our next important topic, periodic current calculation. From this topic, we can expect questions such as, a periodic current changes suddenly from one value to the next at equal time intervals. The values in one complete cycle are 0, 2, 4, 6, 8, 10, 8, 6, 4, 2, 0, -2, -4, -6, -8, -10, -8 and so on. Calculate RMS value, average value, form factor, and peak factor. This type of question involves stepwise calculation of RMS and average by using the definitions of each factor. Alright, let's move on to our next important topic, sinusoidal current calculation. From this topic, we can expect questions such as, a sinusoidal alternating current has an RMS value of 40 amperes and a periodic time of 20 milliseconds. The waveform enters the positive half cycle at time 0. Calculate the instantaneous value of current at 7 milliseconds and 14 milliseconds, the peak value, and the equation for instantaneous current. For such calculations, we use the relation I max equals √2 times RMS and I equals I max sin omega t to find instantaneous values. Alright, let's move on to our next important topic, voltage waveform problem. From this topic, we can expect questions such as, a sinusoidal voltage waveform has a form factor of 1.15 and a peak factor of 1.57. If the maximum voltage is 440 volts, calculate the average value of the voltage, the RMS value, and show the relations of form factor and peak factor used in the calculations. We use the formulas, form factor equals RMS value divided by average value, and peak factor equals maximum value divided by RMS value to solve this. Alright, let's move on to our next important topic, general waveform equation. From this topic, we can expect questions such as, the instantaneous value of an alternating current is given by the equation I equals 7.071 sine of 157.08 t minus pi by 4 amperes. Find the RMS value of the current, the periodic time of the waveform, the instant at which the current reaches its positive maximum value, and sketch the waveform over one complete cycle. From the equation we identify I max, then use it to find RMS and period using the relation omega equals 2 pi f. The phase shift tells us the starting position of the waveform. Alright, let's move on to our next important topic, phase and phase difference. From this topic, we can expect questions such as, explain the concept of phase and phase difference with suitable phasor diagrams. A 50 Hz alternating current has an RMS value of 10 amperes and an instantaneous value of 7.07 amperes at time 0. Write the equation for the current and sketch the waveform stating all current values and the phase angle. Phase represents the angular position of a point on the waveform relative to time 0, and phase difference represents the difference in phase between two waveforms. It can be visualized using phasor diagrams as arrows rotating in a circle. Alright, let's move on to our next important topic, lagging and leading phase. From this topic, we can expect questions such as, differentiate between lagging and leading phase quantities with an example. A waveform is said to be lagging if it reaches its zero crossing or peak later than another waveform, and leading if it reaches earlier. For example, in an inductive circuit, current lags voltage, while in a capacitive circuit, current leads voltage. Alright, let's move on to our next important topic, phasor conversion. From this topic, we can expect questions such as, convert the given phasor quantity into rectangular and polar forms with an example. In AC analysis, phasor quantities can be expressed in rectangular form as x plus jy and in polar form as magnitude at an angle theta. This helps in simplifying calculations in complex circuits. Alright, let's move on to our next important topic, voltage and current relationship. From this topic, we can expect questions such as, derive the voltage and current relationship in an AC circuit with pure resistance, pure inductance, and pure capacitance. In a purely resistive circuit, current and voltage are in phase. In a purely inductive circuit, current lags voltage by 90 degrees. In a purely capacitive circuit, current leads voltage by 90 degrees. These relationships can be represented by phasor diagrams. Alright, let's move on to our next important topic, sinusoidal current with given factors. From this topic, we can expect questions such as, a 50 Hz sinusoidal alternating current has peak factor 1.4, form factor 1.1, average value 20 amperes, and instantaneous value at time 0 is 15 amperes. Express the final equation in proper sinusoidal form. Here, the equation is formed using all given parameters by substituting them into the standard sinusoidal equation. That's all for today's session. These are the most important and expected questions from this unit. Make sure to understand these concepts thoroughly and practice the related numerical problems so you feel fully confident for your semester exams. Hello students. Today we are going to explore Unit 4, AC Circuits. I will keep things very simple and highlight the most important points that will help you score well in your exams. So let's get started with our first important topic. We often deal with phasor quantities in AC circuits. To solve problems, we sometimes need to convert a phasor quantity into rectangular and polar forms. In rectangular form, we express it as x plus jy, where x is the horizontal component and y is the vertical component. In polar form, we express it as a magnitude and an angle. For example, if we have a phasor of 3 plus j4, the magnitude is 5 and the angle is the tangent inverse of 4 by 3. This concept is extremely useful in AC circuit analysis. Alright, let's move on to our next important topic. Derive the voltage and current relationship in an AC circuit with pure resistance, pure inductance, and pure capacitance. In a purely resistive circuit, voltage and current are always in phase, meaning they rise and fall together. In a purely inductive circuit, the current lags behind the voltage by 90 degrees, which means the current reaches its peak later than the voltage. In a purely capacitive circuit, the current leads the voltage by 90 degrees, meaning the current reaches its peak earlier. These phase differences are important because they affect how power behaves in the circuit. Alright, let's move on to our next important topic. Obtain the expression for average power drawn by an RL series circuit when excited with a sinusoidal voltage source. In an RL series circuit, the average power is given by the formula P equals VI cosine phi, where phi is the phase angle between voltage and current. The cosine phi part is called the power factor, and it shows how much of the total power is effectively used. If the power factor is low, less power is actually doing useful work. Alright, let's move on to our next important topic. What is series resonance? Derive the expression for resonant frequency in a series RLC circuit. Series resonance happens when the inductive reactance and capacitive reactance cancel each other out in an RLC circuit. This means the circuit's impedance is minimum and the current becomes maximum at a particular frequency called the resonant frequency. The formula for resonant frequency is F equals 1 over 2 pi square root of LC, where L is inductance and C is capacitance. This condition is very important in tuning circuits like radios. Alright, let's move on to our next important topic. Obtain the expression for power in an RC series circuit when supplied with V equals Vm sin omega t. For an RC series circuit, The power is also given by P equals VI cosine phi. The phase angle phi depends on the ratio of reactance of the capacitor and resistance. A capacitor causes the current to lead the voltage, which affects the power factor of the circuit. Alright, let's move on to our next important topic. Calculate reactance, impedance, current, power factor, active, reactive, and apparent power for a given RLC circuit. In an RLC circuit, the reactance of the induct is given by XL equals to pi FL, and the reactance of the capacitor is given by XC equals 1 over 2 pi FC. The impedance of the circuit is Z equals square root of R squared plus the difference of XL and XC squared. The current is simply I equals V by Z. The active power is the actual power used. Reactive power is the power stored and released. And apparent power is the combination of both. These relationships are often shown in a diagram called the power triangle. Alright, let's move on to our next important topic. Analyze the power triangle and explain the relationship between active, reactive, and apparent power in AC circuits. The power triangle is a right-angled triangle where the base represents active power, the vertical side represents reactive power, and the hypotenuse represents apparent power. The angle between apparent power and active power is the phase angle phi. The cosine of phi gives the power factor. This diagram helps us understand how the circuit consumes power. Alright, let's move on to our next important topic. Define phase sequence and balanced or unbalanced load in three-phase systems. Phase sequence is the order in which the three-phase voltages reach their maximum value. A balanced load means all phases draw equal current and have equal impedance. An unbalanced load means one or more phases have different current or impedance. This concept is essential for analyzing three-phase circuits. Alright, let's move on to our next important topic. State the relationship between line and phase voltage, line and phase current in a star-connected balanced load. In a star connection, the line voltage equals square root of 3 times the phase voltage, and the line current equals the phase current. These relationships are crucial for solving problems in three-phase circuits. Alright, let's move on to our next important topic. Prove that the three-phase delta-connected balanced load consumes thrice the power consumed by the star-connected load. In a delta connection, the line current equals square root of 3 times the phase current, and the line voltage equals the phase voltage. Due to these relationships, a delta connection consumes 3 times more power compared to a star connection when the same line voltage is applied. Alright, let's move on to our next important topic. Sketch voltage and current curves for charging a capacitor through a resistor connected to a DC voltage and derive related expressions. When a capacitor charges through a resistor, the voltage across the capacitor gradually increases and follows an exponential curve, while the current gradually decreases over time. This relationship is described by the equation V equals V0 times 1 minus e to the power minus t by RC. The curves show how energy is stored in the capacitor. Alright, let's move on to our next important topic. Explain and calculate voltages, impedances, and powers for AC systems with specific resistive, inductive, and capacitive loads. In AC systems, we calculate the voltage, impedance, and power by using the relationships of Ohm's law and the power formulas discussed earlier. Each type of load affects the current and phase angle differently, so we must carefully use the appropriate formulas to find the total values. These are the most important questions from Unit 4 AC circuits that you must focus on while preparing for your exams. If you understand these key concepts and practice the related problems, you will be confident and ready to score excellent marks. Students, now we are starting Unit 5, Introduction to Electric Machines. I am going to explain each important question in a very simple and friendly way so that you can easily understand and remember it for your exams. Let us begin with the first question. State and explain the principle of working of a single-phase transformer. A transformer works on the principle of electromagnetic induction. When an alternating current flows through the primary winding, it produces a changing magnetic flux in the core. This changing flux links with the secondary winding and induces an EMF in it. The transformer transfers electrical energy from one circuit to another without changing the frequency. Alright, let's move on to our next important topic. Why are steel laminations used in transformer cores? From this topic, we can expect questions such as sketch different types of laminations used. Steel laminations are used in transformer cores to reduce eddy current losses. Instead of using a solid core, we stack thin sheets of steel called laminations, each separated by a thin layer of insulation. This arrangement prevents large circulating currents in the core and improves the efficiency of the transformer. The laminations can be in shapes like EI type or L type. Alright, let's move on to our next important topic. Derive an expression for EMF induced in a single-phase transformer. From this topic, we can expect questions such as derive the EMF equation of a single-phase transformer and hence obtain the transformation ratio. The EMF equation of a transformer is derived from Faraday's law of electromagnetic induction. The equation is E equals 4.44 times frequency times number of turns times maximum flux. The transformation ratio is the ratio of primary voltage to secondary voltage and it equals the ratio of primary turns to secondary turns. This ratio tells us whether the transformer is step up or step down. Alright, let's move on to our next important topic. The primary winding of a single-phase transformer is connected to a 230-volt, 50 Hz supply. The secondary winding has 1500 turns. If the maximum value of the core flux is 0.00215 Weber, determine the secondary induced EMF, number of turns in the primary, cross-sectional area of the core if the maximum value of flux density is 0.1 Tesla, and also decide whether it is a step-up or step-down transformer. To solve this, we use the EMF equation we just discussed. We substitute the given values to find the secondary EMF, the primary turns, and the area using flux equals flux density times area. By comparing the number of turns or voltages, we can tell if it steps up or steps down the voltage. Alright, let's move on to our next important topic. Compare an auto transformer with a conventional to-winding transformer by mentioning any three differences. An auto transformer has only one winding that acts as both primary and secondary, while a to-winding transformer has separate primary and secondary windings. An auto transformer is lighter, cheaper, and more efficient for small voltage changes, but it does not provide electrical isolation between input and output. Alright, let's move on to our next important topic. What are the losses in a transformer? From this topic, we can expect questions such as state the paths in which they occur and how to minimize them. A transformer mainly has core losses and copper losses. Core losses include hysteresis and eddy current losses that occur in the core. Copper losses happen due to the resistance of windings. We minimize these losses by using good quality steel laminations for the core and by using thick copper wires to reduce resistance. Alright, let's move on to our next important topic. Define voltage regulation and efficiency of a transformer with the formula. Voltage regulation shows the change in secondary voltage from no load to full load condition expressed as a percentage. Efficiency is the ratio of output power to input power, showing how much energy is effectively delivered. Both are very important for evaluating the performance of a transformer. Alright, let's move on to our next important topic. Explain the construction and working principle of a DC motor. A DC motor converts electrical energy into mechanical energy based on the principle that a current-carrying conductor placed in a magnetic field experiences a force. It has a stator that produces the magnetic field and a rotor or armature that rotates when current flows through it. Alright, let's move on to our next important topic. Write the voltage equation of a DC motor and explain its significance. The voltage equation of a DC motor is V equals EB plus IARA, where V is supply voltage, EB is back EMF, IA is armature current, and RA is armature resistance. This equation shows how the supply voltage is divided between back EMF and the voltage drop across the armature. Alright, let's move on to our next important topic. Explain the characteristics of a DC motor and its applications. The main characteristics are speed current, torque current, and speed-torque curves, which help us understand how the motor behaves under load. DC motors are used in electric traction, cranes, lifts, and many industrial machines where precise speed control is needed. Alright, let's move on to our next important topic. Explain the working principle of a three-phase induction motor using rotating magnetic field theory. A three-phase induction motor works on the principle that a rotating magnetic field is produced in the stator when a three-phase supply is given. This rotating field cuts the rotor conductors and induces a current in them, which creates another magnetic field. The interaction of these fields produces torque and makes the rotor rotate. Alright, let's move on to our next important topic. Explain the types of three-phase induction motors and their applications. There are two main types, squirrel cage and slip ring induction motors. Squirrel cage motors are rugged, cheap, and used in fans, pumps, and compressors. Slip ring motors allow external resistance for better speed control and are used in heavy machinery. Alright, let's move on to our next important topic. Explain the construction and working principle of a single-phase induction motor. A single-phase induction motor has a stator with a single-phase winding and a rotor similar to a squirrel cage. It works on the principle of double revolving field theory and requires a starting mechanism to begin rotation because a single-phase supply alone cannot produce a rotating field. Alright, let's move on to our next important topic. Explain the applications of split-phase, capacitor start, and capacitor in motors. Split-phase motors are used in washing machines and small tools. Capacitor start motors are suitable for high starting torque applications like compressors and pumps. Capacitor in motors run smoothly and efficiently in fans and blowers. Alright, let's move on to our next important topic. State the material used for positive plate, negative plate, and electrolyte in a lead-acid battery. The positive plate is made of lead dioxide, the negative plate is made of sponge lead, and the electrolyte is dilute sulfuric acid. Alright, let's move on to our next important topic. Explain the construction, working, maintenance procedure, and any two applications of a lead-acid battery. A lead-acid battery has lead dioxide and sponge lead plates immersed in dilute sulfuric acid. During discharge, chemical reactions produce electrical energy, and during charging, the reactions reverse. Maintenance includes keeping the plates covered with electrolyte and cleaning the terminals. They are used in automobiles and backup power supplies. Alright, let's move on to our next important topic. Compare a lead-acid battery and a lithium-ion battery by mentioning 6 points. A lithium-ion battery is lighter, has higher energy density, charges faster, has longer life, requires less maintenance, and is more eco-friendly compared to a lead-acid battery. Alright, let's move on to our next important topic. Explain the operation of a lithium-ion battery with construction and chemical reactions during charging and discharging. Also, state its applications. A lithium-ion battery has a cathode usually made of lithium cobalt oxide, an anode made of graphite, and an electrolyte that allows lithium ions to move. During charging, lithium ions move from cathode to anode, and during discharging, they move back from anode to cathode, releasing energy. These batteries are used in mobile phones, laptops, and electric vehicles. Alright, let's move on to our next important topic. Specify the cathode material, anode material, and electrolyte material in a lithium-ion battery. The cathode is typically lithium cobalt oxide, the anode is graphite, and the electrolyte is a lithium salt inorganic solvent. These are all the important questions from Unit 5, Introduction to Electric Machines. If you understand these concepts well and practice problems related to them, you will surely do great in your exams.